converting access ports on a switch to full-blown 802.1q trunk ports through the magic of dynamic trunking protocol. Let's begin. I'd like you to take a look with me at this network topology. We've got VLAN 10, which is associated with an IP subnet. That's very likely what we're going to see in most networks is one VLAN per one subnet address. That's great. And we've got VLAN 20 right here, and these are all user systems. And so we have two groups of users, and we also have another VLAN for a server or servers. Now, why in the world would we separate them into separate networks? Well, one reason, very likely, might be we have hundreds of devices. We just don't want a huge IP version 4 broadcast domain. That's one possibility. But a more likely scenario of why we divided them up is for security reasons. See, if we have users in VLAN 10 and VLAN 20, and we want to control what ports are available to go between those VLANs and the server VLANs, we can use an access control list on a router. And that's fantastic. So in this case, we might have, for example, this is a trunked interface. This red line represents a trunk. And on R1, we have sub interfaces. We have one for VLAN 10, one for VLAN 20, one for VLAN 30. And as such, router 1 can route between them. So when traffic needs to go between VLAN 10 and VLAN 30, the traffic would go like this. It would go over to its default gateway. The router would say, oh, I know how to reach VLAN 30. It would re-encapsulate the layer 2 frames and send them over. At the same time, R1 has the opportunity to check access control list to verify whether or not packets based on layer 4 protocols or ports involved or source and destination IP addresses, whether or not that traffic is allowed. So this guy right here is the security enforcer regarding what traffic, transit traffic, is going to make it between the various VLANs. So that's great, Keith. Why do you bring that up? Well, I bring that up because perhaps you and I might want to look at a way of bypassing the ACL on this router. What if we could logically put this PC on the same subnet as that server, and then any type of attack could be run? Or for example, if this VLAN was never supposed to access the servers on VLAN 30 and an access control list was stopping it, if we put this computer on the same VLAN 30, there's no longer an access list at this router that we have to deal with. So how could we pull that off? One way we could go ahead and put this computer directly on this VLAN is to call the administrator and say, hey, can you change gigabit 0/3 from an access port and on VLAN 10 and make it an access port on VLAN 30. Not very likely they're going to go for it, especially for an attacker. So instead of doing that, what we could do is hope that they haven't secured their switch. And if they haven't secured their switch, and if their switch is in an attitude of using DTP to dynamically negotiate this port, whether it's an access port or a trunk port, we can simply run backtrack here. We can send in DTP, and DTP is an acronym. It stands for Dynamic Trunking Protocol. And if this guy's in an attitude of being willing to negotiate whether it's an access port or a trunk port, if we send in DTP messages saying, hey, we want to be a trunk, we want to be a trunk, that guy will flip over and automatically become a trunk for us. Now, this would be a lack of proper configuration on the switch, but there's a boatload of switches that are by default set to dynamically negotiate that trunk. So all we have to do is pretend that we're a switch or another device that is trunking by sending DTP in, and poof, it's a trunk. So with that, this link now changes to red, meaning it's a trunk link, and now it's carrying VLAN 20 traffic, VLAN 30 traffic, and then all we need to do on the backtrack system is we need to load up the actual support for 802.1q. That's the mechanism for tagging frames for doing trunking, and create some sub interfaces on our backtrack system, and we can create one for VLAN 20 and VLAN 30, and we can actually have interfaces, logical interfaces, on every single VLAN that we want. And once we have an interface on VLAN 30, we can then go ahead and communicate directly with the other devices on that VLAN and not have to go through the router. This is a really serious problem if somebody on your network is doing this because they've just bypassed all of your local access control list security. So let me give you a little backstory on setting this up. Now I have a computer, an external laptop that is physically connected to a switch, and I also have a Windows computer right here. And using the technique that we discussed in our previous nugget, I am using SSH, and I'm also running the Xming X Windows server on my Windows box. That way I can remote control this device effectively with SSH and also taking advantage of the X Windows redirect back to this computer and also record it, which is the primary reason. So unless you're doing recording software, you can just do this directly on the laptop itself. I would also like to share with you that I actually had to swap out this laptop for a different laptop. The first one, the one I was using in a previous Nugget, which is an IBM Lenovo, not just a really old laptop. It wasn't properly processing the tags. It wasn't doing the 802.1q. And for the life of me, I think it just must be the actual hardware they used for the network interface card. It wouldn't send them. It would do all the other tags, HSRP and spanning tree, and it would even send DTP messages, but it wouldn't actually start tagging, no matter how hard I tried with a couple different tool sets. So I swapped it out with a different IBM laptop, a different model, and it works. Now, why do I point that out? I point that out because not every computer, Windows or Linux or Backtrack, not every Ethernet adapter is going to be happy and successful by processing .1q frames and actually injecting them as part of the flow of traffic. So before you actually go out and do your authorized pen testing, you may want to, in a test environment, verify that the hardware that you plan to use actually supports it. So you might ask, well, Keith, how do we verify that .1q tagging is working on the hardware I plan to use? And the answer is, try it. So you can walk through the exact steps that you're going to see us do here in this Nugget. And if you can successfully ping on other VLANs with your sub interfaces, you know that your hardware is correctly working for that tagging functionality. One other thing I think is important that you know about this second laptop is that I didn't take the full time to do a full install to the hard drive of that computer. I simply said, you know what, I want to test this. So I just popped in the live CD, booted from it, and I went to the GUI interface with StartX. I actually set up a new password for administrator. By the way, the command for that is PASSWD. So if you want to change your password once you're logged on, just type in PASSWD. It'll say, great, what do you want to change it to? Confirm it, and you're set. So I did set the password to Tour, because by default on the boot CD there is no password. I needed one for SSH access. I ran SSHD generate, just like we have in a previous Nugget, so I could have SSH support. And I also configured the wireless interface on that system. That's because I'm using the Ethernet to go ahead and communicate with the switch on port gig03. So I needed wireless access so I could have remote access via SSH and X Windows support over to that device. And then I launched SSH, and I have the Xming server, also from the previous video, that I'm running on my Windows computer. And as a result, if I launch a GUI from here now, just like Yersinia, as we have previously, the output is redirected back to my Windows box. Now, why would I do all those extra steps? And the answer is, my friend, for you, because I wanted to record this and be able to share it with you. If you don't need remote access, you could simply do all of it right here. And you wouldn't need the SSH, and you wouldn't need the Xming or anything else. You could do it all from the GUI of that laptop device. So let me introduce you to the hardware. Right here we have this Catalyst 3560G switch, and I've got a Backtrack system. This is the laptop running the live CD, and it's physically connected. It's Ethernet 0 is connected to port gigabit 0/3. That's a G right there for gigabit, and that's the actual switch itself. Now, connecting to the Backtrack, I'm using SSH to connect to that Backtrack, and I'm going to do it a couple times. I've got an SSH session here from Secure CRT. I've also got another window with SSH running from PuTTY. It's the PuTTY that I've got configured with the X Windows redirection back to my machine. So I've got this window for just basic commands, and the other window we'll use for launching the graphical Yersinia with the -G option. I've also got connectivity to a router in the event we need it, but that's the basic connectivity for this demonstration in this test network. So on this switch, let's go ahead and take a look and see if it has any currently active trunk ports, and it shouldn't, because I've got no other Cisco devices, nobody else is trunking, nobody's sending DTP. Another thing that I think will be useful for us is let's take a look at the functional status right now of gig 0/3, that interface. That's where our Backtrack system is physically connected. I've also done an exclude on the output just to remove some of the clutter right here. If you just want to do this command, show interface gig 0/3 switch port, it'll show you all the details about it. The exclude, again, is just to reduce some of the clutter from the output. And what this is showing us is that administratively means how it's configured, and operational means how it's working at the moment. So this interface, gig 03, is administratively configured as dynamic, meaning it'll be willing to negotiate trunking. Desirable says, hey, I'm willing to be a trunk. Auto says, I'll be a trunk in case somebody asks me. It really doesn't matter if they're desirable or auto, because we're going to send DTP messages saying, yes, we would like to go ahead and be a trunk with you from the Backtrack system. This, my friends, is a mistake. You should never leave a port being willing on its own to determine, yeah, I'll be a trunk, or no, I'm going to be an access port. You want to control that and lock it down hard. In this case, it's not administratively locked down. It's set up as desirable, which a lot of switches are by default, which is a huge problem as well. And it's currently operating in access port mode. So it's an access port associated with VLAN 10, and that's currently how it is. However, if we send in a DTP frame, it will flip over and become a trunk port. Also, just for grins, let's take a look at the IP addresses. Show IP interface brief, exclude unassigned, is just so that you and I don't have to look through the entire list of all the interfaces on the switch that don't have an IP address. That's all it is. So I've got an IP address on VLAN 1. I've got an IP address on interface VLAN 10, 20, and 30. Now, an attacker would not have direct access to this. However, it'd be fairly simple to determine what those addresses are. I'll show you how to do that as well. So here are the IP addresses on each of the respective VLANs. Also, at the moment, it shows these two interfaces, the 30 and the 20, as being down. So it says, I've got these basic interfaces. However, I've got no other ports associated with those VLANs. It's like having no one to talk to. So I'm just going to go hide until there's a port. So if we bring up a trunk that's allowing VLANs 20 and 30, that would trigger these interfaces to come up. Or if we assigned other ports that are up to VLANs 20 or 30, that would also cause them to pop up. One last thing I'd like to do is I'm going to turn on some very simple debugging of DTP events. And this is pretty much just for the confirmation factor. If we launch an attack and then we can also see the direct reaction on the switch, that's just another confirmation that it's actually working. Again, if we're an attacker, we're not going to have access to we're not initially going to have access to the command line interface of the switch until we compromise it. However, using these tools is just going to help reinforce the attack that it's working. So this is my PuTTY window right here. And do you remember why we're using PuTTY? And the primary reason we're using PuTTY is because it has that option for doing redirection of X windows back to this host machine. So if I'm running PuTTY here, if I launch, for example, Yersinia-G on this computer, that will launch the graphical interface from the backtrack system and redirect the output over to a new window on this computer. That's the primary reason I'm using it. Now, I actually could have run X11 redirection from this guy as well if I'd configured it, but I'm going to use this for any basic command line interface action we need, and I'm going to use this window just to launch any graphical applications on that remote machine. So having said that, let's launch Yersinia -G, because we want the graphical user interface version of it, and that's going to launch it and bring up a new window, and that's the window that we're looking at right now. So in the background, I'm going to go ahead and minimize the actual SSH session that launched it. Is still open, so I'm going to put that in the background, and let's go ahead and focus on our attack. And then we can see everything right here. This is fantastic. We have the debug window right here happening. To do dynamic trunking, it's showing us right here what the attitude is of the switch. It says, yeah, I got a DTP frame in. I've got one of them. That'll increase as we go on. And it currently says, yeah, he's currently set up as an access port, but he's desirable, meaning he's willing to negotiate a trunk with us. All we need to do is send down a DTP packet, and he'll flip over to trunk status. So let's actually do that. Let's launch attack, and we'll simply say I want under DTP. I'm not just going to send a DTP packet and flip him. I actually want to do trunking. And this will periodically send DTP messages just to give comfort to the far side saying, yeah, you're still a trunk. Let's be a trunk, and you're fine. So let's go ahead and launch this. And down here on the left, you'll notice I have my debug that just outputs some details regarding these messages being sent. So we've just sent DTP, and this switch has just converted that interface over to a trunk. So let's go ahead and do a up arrow key a couple of times, and let's do a show interface trunk. So now what it's saying is, yeah, I'm gig 0/3 is a trunk, and I'm using 802.1q. It's currently trunking, and the VLANs allowed are VLANs 1, 10, 20, 30, and 40. Now, this right here is very important. VLANs in spanning tree forwarding state and not pruned. What does that mean? Well, spanning tree by default is going to take like 30 seconds just to be safe that we don't have a parallel path. And after 30 seconds, this should flip over, and he should start forwarding on those as well. So for the first 30 seconds, if they're using the old default spanning tree, not rapid spanning tree or anything else like that, we're going to have a little delay there. So let me take off my pen. So what just happened was spanning tree allowed those ports to start forwarding, and that's what happened right here. So these logical interfaces came up now. Now VLANs 1, 20, and 30 came up because we now have a trunk that's allowing those VLANs. And as a result, those interfaces can now be up along with VLAN 10, which was already up. I've also got, look at this. I've got HSRP running on both VLANs. So it's running on VLAN 10, 20, and 30. The HSRP for VLAN 10 was already going. We attacked that in a previous nugget. And now VLAN 20 and 30, because it has an interface, a trunk that's supporting those, it's now brought those up as well, and it's the active unit. So this switch is acting as the HSRP active device for, based on the results, VLANs 10, 20, and 30. This message right here is from our debug. We're just pumping in those DTPs periodically to keep that other side happy, happy, happy. Now let's go back to our graphical user interface right here, and you'll notice that our 802.1q traffic is now increasing. That's because every frame it sees that it now has the 802.1q tag it's processing. So if we want to go back to 802.1q right here, this tab, this is going to show us what it knows about. So we have VLAN 10, VLAN 30, VLAN 20, and that's how we could know what VLANs are out there. We just ask it. We could also launch Wireshark and just take a look at the .1q tags. Several different ways of knowing exactly which VLANs are there. Now, a lot of this traffic also is the HSRP that's happening. So we have the source IP addresses of these guys, and they're just simply telling us who they are. So we pause this. This is the switch's address right here that we saw earlier. This is the router. That's R1. And, oh, here we go. Here's the virtual address advertised by HSRP. Fantastic. One for each VLAN. Fantastic. So now our challenge is, how do we get ourselves onto any VLAN that we want to? And that's actually pretty simple. All we're going to do is create logical sub-interfaces and tell it to do trunking on those interfaces, and we can logically be on any one of those VLANs and assign ourselves an appropriate IP address based on the subnet information that we're seeing right here. So for VLAN 20, they're using the 20 network. For VLAN 30, they're using the 30 network. Now, is there a possibility if we just grab and administratively configure an IP address, we might be in conflict with somebody? Yes. Yes, but there's a good opportunity, a good possibility if you don't choose like .1 or .161 here. Those are listed. It's very likely you pick something in the high-end range, you're not going to conflict with anybody else who's currently on that network. And if you are, you can change it to another one until you find a free one. So let's minimize the GUI out of the way just for a moment, and let's go over to our backtrack system. And this is just a plain old SSH session. So I've got one SSH session that I launched through PuTTY that initiated the X Windows output, and this is just a normal SSH session over to the backtrack system. So let's turn on support on this backtrack system for 802.1q tagging. It's really easy. It's modprobe space 802.1q. If you're from a Cisco environment, you have to force yourself not to put in that period between the 1 and the q. In any event, that's the syntax that enables the .1q tagging functionality. And now the problem is, how do we create new logical sub-interfaces that are responding and appropriate for each of those VLANs? And the cool part is there's only one new command, and all the rest you already know. So we're going to do vconfig to create a logical sub-interface off of Ethernet 0. And the 20 represents, yep, this is going to be for VLAN 20, the 802.1q tag of 20. And then we use ifconfig to bring it up, to assign an IP address. So our next question is, how do we know it's actually working? Well, we saw in the output under the 802.1q tab, we saw a couple of IP addresses. We could try to ping those. If we wanted to find out everybody who's currently on that network, one approach to doing that is doing a broadcast ping. And that will ping everybody on the 20.0.0 network. So let's do a quick check. Let's just do an ifconfig on that interface just to verify the IP address took, and it did. And let's do a ping, a broadcast ping. And anybody who responds, we know they're on that network segment. So I'm going to do a Control-C. So let's do that again. Let's add another interface for VLAN 30 and do another broadcast ping as well. So you can create virtual interfaces all day, all night. And to do that, we're going to do a vconfig again. Say I want to add for Ethernet 0, one for the .1q tags of 30, and then the ifconfig to bring it up, give it an IP address, and then we do a broadcast ping of the 30 network. And we should have 30.0.0.161, that's our multi-layer switch, also responding to that. Another option, which is pretty cool, if you didn't want to create sub-interfaces and generate traffic with a trunk up, you can still hear quite a bit of traffic for each of those networks. Any broadcasts, for examples, or unknowns on any of those VLANs are going to be forwarded through the trunk. So if you wanted to capture that, there's two ways of doing it. Number one, you could just kick off a Wireshark, and that would show you everything on that interface. Or you could use this option right here and say capture all protocols And that's yet another way to capture that information. If you select this option, it'll ask you what file do you want to put it in. You'll specify the file name, and then you go open up that file with Wireshark to see the capture. So what I did is I told this machine to go ahead and capture traffic for just a few seconds, and then I copied that file via FTP off of this local backtrack system over back to my Windows host. And I'd like to show you that output real quick. Also, I've saved that capture file in the Nugget Lab download area. So if you'd like to take a closer look at it yourself, you can do so. So let's take a look at that traffic. This is all coming in on the trunked interface now of our backtrack system. And so I've got some spanning tree protocol, that's great. I've got a whole bunch of HSRP, that's fine too. But if you look at any one of these packets, let's grab this one for example, and open it up, you'll see it has the 802.1q header in it, and it's tagged. So basically there's the tag ID right there of 30. If we look at one from VLAN 10, it should be tagged with VLAN 10. And if we look at one 420, it should be tagged with VLAN 20, which it is. So effectively, by creating our sub interfaces, we can join any one of those VLANs and logically be directly connected to each and every one that shows up on that trunk. In this video, you and I have taken a look at how we can trick, really, that's what we're doing, trick an access port on a switch to become a trunk simply by manipulating dynamic trunking protocol messages. And then once we have a trunk established, holy schnikers, we can then go ahead and create sub interfaces and have direct connectivity to any of the VLANs on that trunk. Now, a really important question is, how could we have prevented this or mitigated this type of an attack? And the answer is simple. There's some basic switching security that everybody ought to be doing. First of all, do not let your ports negotiate at all. If they're going to be an access port, you hard code them. If you're going to be a trunk port, you hard code them, and turn off DTP. Turn off the whole negotiation process and say, you know what, this is what you're born to do. This is what you're doing. No matter what DTP shows up, don't pay attention. This is what you're going to do. Another good common security practice for switches is to take all of the ports that are currently not in use and do two things. Number one, shut them down, and number two, assign them to an unused VLAN, like VLAN 999, assuming that's not used in your environment. That way, if somebody does get physical access to ports on the switch, they are not going to lead to anything useful for them. So those are some basic security techniques that we can use to improve our security posture as well. I've had a great time. I appreciate you joining me. I hope this has been informative for you, and I'd like to thank you for viewing. Implementing a man-in-the-middle attack using address resolution protocol spoofing. Let's begin. Have you ever looked at a computer and wondered, I wonder what that computer does all day with that user in front of it? Well, one way of finding out is implementing some ARP spoofing to do a man-in-the-middle attack. Now, ARP is an acronym that stands for Address Resolution Protocol. And what basically happens is on IP networks, IP version 4, we have IP addresses. For example, this PC right here, maybe it's 10.0.0.2. That's its IP address. And the default gateway, the firewall in this case, maybe it's .1 on that network. And it has another IP address on the outside. Well, if this PC wants to forward traffic to its default gateway, which in this case is the firewall, it needs to know the Ethernet layer 2 address. And to find out, it uses ARP. It goes something like this. An ARP request goes out, says, hey, everybody, it's a broadcast. I'm looking for the person who owns 10.0.0.1. If that's you, please give me an ARP reply with your layer 2 address. And the firewall would respond, and now the layer 3 to layer 2 mapping is in the ARP cache of this PC. A similar function happens up here on the firewall if it needs to discover the layer 2 address of some other device on the network that it wants to talk to. So how exactly does an ARP spoofing attack work? We're going to lie about the layer 3 to layer 2 mapping. So for this discussion, let's say this guy is .1, that's the IP address, and this guy is .2. And let's also say that the MAC address is up here, 000011111111 for that interface on the firewall, and the PC's MAC address administratively configured as A, sound like Fonzie, A. Okay, so let's say those are the addresses involved. And they both know it. They've done their own ARP resolution. They know how to reach each other. If we want to put this backtrack machine as a man in the middle, all we have to do is lie to this guy and lie to this guy. And let's say that our MAC address is something like 0000 CC1E6783. All we need to do is have the backtrack machine tell this firewall, hey, dear Mr. 10.0.0.1, the MAC address of 10.0.0.2 is this guy. So in his MAC address table, in his cache, it's going to say, okay, great, to reach 2.2, I'm going to use this layer 2 address. And now any traffic that the firewall is trying to forward to dot 2 is going to be forwarded at layer 2 by the switch network over to the backtrack device. That's half of the problem. The other half is we also need to lie to this guy. So we'll go to the PC and we'll say, hey, with ARP packets, hey, this is 10001 talking. Here's my layer 2 address. And it is 0000CC1E6783. And so effectively, this PC will believe that its default gateway's MAC address is this, the attacker, and the default gateway will believe that the layer 2 address of the PC is also the attacker. And guess what? All the layer 2 frames are going to be forwarded through the backtrack device. Now, as a courtesy, of course, we want to make sure we're forwarding those frames on to the final destination so that we don't cause a complete denial of service. And that could be another reason we do the ARP spoofing, is simply to cause a complete failure of the PC to reach this default gateway. But if we want to route the traffic, all we need to do is set forwarding to on, and we can route it. So a typical transaction with ARP spoofing involved would be the PC, if it wants to go out to Google, for example, the frame would be sent to the backtrack's MAC address. The backtrack, we would go ahead and forward it to the default gateway, and then the default gateway would route it out to Google. Packet comes back, and the return traffic is going to go back to backtrack, and then we'll go ahead and forward it to the PC. You know, we don't want to stop service, perhaps, but we absolutely are doing a man in the middle by simply lying to both devices regarding the layer 2 address of the other devices on the network. The tools we're going to use to implement this, first we're going to use Nmap, because if we have a backtrack system, we need to know what the devices are on the network. So we'll do a quick scan to find out what the other devices are on that network. Then we use ARP spoof. We're going to use it twice. We're going to use once against this target and once against this target to lie and tell both of them that the corresponding IP address of the other device is really the backtrack layer 2 address, and they'll believe it. And then we're going to use DriftNet, which is fantastic in URL Snarf. DriftNet, oh my gosh, it's going to open up a separate window, and any traffic that we eavesdrop upon is going to be automatically be placed in that window, any graphics. So if you're curious about the graphics on the websites that people are going to, they'll pop right up on the backtrack system. And URL Snarf gives us all the nitty-gritty details of exactly the URLs they're going to and the versions of web software that are used on that device. It's fascinating, and we'll take a look at both of those. The main reason they're bringing these two right here is because I want to just demonstrate some additional functionality. I mean, even without these, we could just put on Wireshark, eavesdrop, and see all the traffic as far as what's going on between the client and the external resources that he's accessing. So let's start by introducing the players here. This is a Windows XP machine that's currently sitting on the 10 network, and let's just verify its IP address with an IP config, and that looks good. It's at 10.0.0.2, which is great. If we do a ARP-A, it currently knows about 10.0.0.1, which is its default gateway, which is the firewall. And if we do an IP config /all right here, we can also verify the layer 2 address that we're currently using on this system. So there's the layer 2 address right there. I administratively configured that just to be really easy to recognize. Next, let's take a look at the firewall as well. Let's do a show ARP. This happens to be an adaptive security appliance, and it's showing here that it knows about a couple of MAC addresses, 2 on the inside, 2 on the outside, but it does definitely know about the Windows PC at 10.0.0.2 and its layer 2 address, which is 0.0.0.0 AAAA. This 10.0.0.4, by the way, that's our backtrack system, which is about to do an ARP poisoning attack against the firewall and against the PC at 10.0.0.2. So if we're on this network and we're not sure about exactly which devices are there, we can use a previous tool like Nmap just to verify who's there. So Nmap-F, that's going to search the top 100 ports, and let's search that whole range, the whole 10 network. And it found everybody. So I don't have that many devices there, but it didn't take that long either way. So it found 10.0.0.1, which is my ASA firewall, and it says, oh, he's got 4.4.3 open for management purposes. And then it also found 10.0.0.2, which is our Windows XP machine. It also found 10.0.0.4, which is our backtrack system. And it also found 10.0.0.55. So 10.0.0.5, it's got the X11 service running. That's for the Xming. That happens to be my host computer that I also have placed on this network. So the two that we're going to focus on are these guys, the default gateway and the actual IP address of the little XP box that's going out to the internet. One other thing to do before we actually do the ARP spoofing is let's just make sure we have basic connectivity to the internet to begin with. So we'll open up a browser and let's see what's in our history. Google. All right, so let's go to google.com. Just wanted to make sure that we have functionality before we start implementing the attacks, and it looks like we do. On the Backtrack system, we've already done this previously in a previous nugget, but in case you didn't do that lab and you're just doing this fresh, I want to make sure we're doing forwarding, because if we're doing a man-in-the-middle attack and somebody sends us a frame, if we're not enabling routing on our Backtrack system, we're not going to be willing to forward it out that same interface and onto its true default gateway so it can be routed the rest of the way. So we want to make sure we have a 1 set there. So even if it was already a 1, if you echo a 1 to that file again, it's not going to hurt anything. If we wanted to verify, which is not a bad idea, to make sure that the command we thought was working does, let's go ahead and just do a more of that file and just verify that we have a 1 there. So we are basically now willing to route IP packets for other people. The first half of the ARP spoofing, we're going to aim right at 10.0.0.2. We're basically going to say, hey, guess what? If you're looking for the layer 2 address of 10.0.0.1, it's my address, says the Backtrack system. This is now saying, hey, guess what? The MAC address for 10.0.0.1 is, and it lists the Backtrack system's MAC address, the one that ends in 6783. And then I just let that run. We're just going to poison the ARP caches, lying over and over and over again, and just going to leave that running in one window. Let's go to a second window because we also need to lie to the firewall itself. And to do that, we're going to say arpspoof-i, specifying the interface that we want to use, which in our case is Ethernet 0. We're going to say, okay, dear Mr. 10.0.0.1, you are the victim. And what we're going to do is, anytime you need to reach 10.0.0.2, whatever MAC address you had for 10.0.0.2, it's not true. It's really our MAC address. And again, we're lying one more time, specifying that it's the MAC address ending in 6783. So if we leave both of those running, which I'm going to, by the way, let's go ahead and take a look at the ASA. And just a moment ago, or a few minutes ago, this was the ARP cache. This is the accurate ARP cache, by the way, where this device, the firewall, believes to reach 10.0.0.2, it can reach it at the layer 2 address with all the A's in it. Well, now that we've poisoned the ARP cache of the firewall for that entry, if we simply use an up arrow key and bring that up again, check this out. It now says, oh, to reach 10.0.0.2, the MAC address I should use is the Backtrack system. And it will use it. At layer 2, it just forwards it, encapsulates the frame, sends it, and it sends it right to our Backtrack system. And we also could look at the PC. Let's go ahead and do that real quick. So on our PC, when we did the ARP-A, it said, okay, to reach 10.0.0.1, the MAC address is this. So in the ARP cache of the PC, it says, okay, to reach 10.0.0.1, what I used to know, or what I believed anyway, was the address of 00ABCD. This is also administratively configured. This is the MAC address that I would use to reach my default gateway of 10.0.0.1. But now that we're running the ARP poisoning attack against it as well, check this out. We'll go ahead and hit the up arrow key a couple times, and now it says, oh, to reach 10.0.0.1, I know how to get there. And that's the Backtrack machine's MAC address. So effectively, we're doing ARP spoofing against the default gateway regarding the PC at 10.0.0.2, and we're doing ARP spoofing against the PC regarding its ARP entry of its default gateway at 10.0.0.1. We're effectively now a man in the middle. So now that we've got the man in the middle attack working, or we think it's working, let's verify it. Let's go ahead and open up a couple windows inside of Backtrack. The first one we'll do driftnet-i. Again, to get context-sensitive help with any of these commands, it's driftnet space -h, and it'll give you the syntax. The -i represents we were going to listen to and pay attention to the traffic we see on Ethernet 0, and that's going to open up a separate window. Let me show you. And this separate window right here is where the graphics are going to pop in. So that customer that we're doing the man in the middle against, as he goes out and visits sites, any graphic images are going to be popped into this one. Now, does that mean every single graphic image? The answer is no. If he's going up through SSL or some other encrypted technology to a website, of course we can't see the encrypted data, but any plain text images certainly will pop in right there. The other tool we're going to launch is URL Snarf right here. And URL Snarf is simply going to give us the details on all the URLs that customer happens to be going to. So we'll launch that one as well. So with both of those running, and let me make this window a little bit bigger to make it a little bit more fun, let's bring in our victim. So here's our little Windows XP box, and let's open up a browser. So we'll open up a browser, and let's just go out to www.google.com. So as we go out to google.com, As we go to google.com, this window up here is taking a look at all the details. And over here, we have the graphical images that are being pulled down. So if we search for example, I think my name is pretty safe, Keith Barker, CCIE, press enter. The images that come in, yeah, that's mostly me. So yeah, in fact, these 4 are me. And they're somewhere on the pages that got pulled down. If we went to images and did that same kind of search, we would get even more. So most of these people are me, and there's a few that aren't me, but there you have it. And that's the graphical images that are being pulled down from that customer on this PC right here and showing up on our Backtrack system in a separate window. One other really cool thing we could do is Wireshark. I mean, Wireshark would allow us to see not only the URLs being visited and the graphics that are being pulled down, but also we could see every ounce of every packet that's going between the client and the internet. In fact, we should do that too since we're right here. So we'll simply bring up a command line and we'll simply type in Wireshark. And that'll bring up Wireshark. And on Wireshark, we'll say we want to go ahead and we want to make this window bigger, first of all. And we want to listen on Ethernet 0. Please start. It'll start capturing traffic. We'll go back to our client here. And on this client page, we'll go out to www.cisco.com, for example, or something else. And then we'll go ahead and stop that because it's going to rotate pages periodically. And here's all the traffic. So if we go back here and stop the madness, because there's a lot of traffic, and that was quite a bit of traffic. We got over close to 3,000 packets in those few seconds right there. So yet another way to take a closer look on exactly the data that's involved. And if the client had logged in through HTTP or done other clear text applications like FTP where they used a username or a password, we would be able to capture every ounce of that, and those passwords would then be known to us. Now, if we're done with the attack, we really don't want all that traffic coursing through our Backtrack. So when we're done, we can just do a Control-C, and I want you to take a look at the very bottom of the screen right here. What it's going to do, it's going to repopulate with the correct ARP entries right here. It's like restoring it back to normal before we did the attack, and we'll go do it on the other system as well. So the Control-C takes a few seconds, and it repopulates the correct information. And that's the ARP entries that should be in place before we started doing the man-in-the-middle and the ARP spoofing. In this video, we've identified how we can implement an ARP spoofing attack using this primary tool of ARP spoof. The DriftNet and the URL Snarf and Wireshark are just great ways of seeing that content and what's going on, but the actual tool to implement it was ARP spoof. We also used Nmap to identify the devices on a network so we could go ahead and implement the man-in-the-middle attack. I also want to point out that there's some routers out there. Let's say that we had, instead of using a firewall, let's say it's a router. Let's say it's R1, and its address is 10.0.0.1. Some routers, not all, but some routers, when they see that there's ARP spoofing happening, and how would they know that? Well, for example, it knows its MAC address. It knows that its IP address is 10.0.0.1. If it sees messages that are telling the network, the rest of the network, hey, my IP address is 10.0.0.1 and my layer 2 address. So we had 2 examples of using the MSF console, which is fine and great. I do want to share with you this graphical user interface that is fantastic. You have access to virtually everything you do at the command line, but because it's GUI based and gives you menus to select from, in my opinion, it gives you more visibility to the potential options that you'd be using when you're running Metasploit. Let's take a look at the GUI. To actually run Armitage, there's 2 ways of doing it. You simply open up a command line and say Armitage, and that would launch it. Or if you wanted to use the menu, you could find it that way too. We'll go up to Backtrack and go to Exploitation Tools right here. And then we'll go down to Network Exploitation Tools, go down to Metasploit Framework, and then we can go down to Armitage right here. So it's 5 menus deep, or you could just open a command line and type in Armitage. Either way is great. And what this does, it automates all the details that we don't have to worry about. For example, it's automatically going to connect to itself. 127.0.0.1 is a loopback. It knows the port it's going to use. It's going to create a user and password. It's all done in the background. So we can just launch it and it'll do it. It's also going to say, you know what? The RPC server isn't running that's needed for this. Do you want me to let it run? Yes. And it launches it for you. So you don't have to do any of that. And it's going to go ahead and connect here in a few seconds. And there we have it, Armitage. So for me, we have this really nice graphical user interface. And check it out, we still have the MSF console down here. So you can still do your MSF commands, everything else you'd want, but you also have access. For example, let's do that SYNFLET attack one more time. If we wanted to do it, we can just go to Auxiliary. and then under DOS, I'll just double click to open that up, and then scroll down to TCP and SYNFLET right there. So now that we're here, we just double click on that. Check it out. It gives us all the options to put that same information back in. So if we want to specify the remote host of 192.168.1.50 and we want to use a source host address of 10.0.0.50, again, just like we had previously, specify any other details, click on launch, it's going to go ahead and launch that same attack for us. And now that attack is running once more. If we bring back the firewall and we take a look at the show connection count again, it's on the rise, steadily increasing. And that's because the attack is now running. So whether you want to use MSF Console or you want to use Armitage, it really doesn't matter. You're going to have a lot of the same functionality in each of the platforms. In this nugget, we've taken a look at a couple of really important things. Number one, how to make sure Metasploit is installed on the Backtrack so we can use it. And secondly, we've investigated a couple of different interfaces that we can use. The graphical Armitage, I feel, is very, very convenient and handy, but we also have the MSF Console that we can use. We demonstrated from both interfaces a SYNFLET attack and the very similar results we're going to get regardless of the interface that we choose to use. The actual parameters that I used in this demo, I've put in the Nugget Lab area for download, so you can have those if you want. I do want to point out that if you are using any of these tools and there's the potential for traffic to aggressively leak out, for example, with the SYNFLET attack, with by default randomized source addresses, you definitely want to close down that internet-facing port on your switch or router so that you're not accidentally sending traffic that shouldn't be going on the internet in that direction. Play it safe. I've had a great time. I'm glad you joined me. I hope this has been informative for you, and I'd like to thank you for viewing.